before we move on to our main topic, we will going to have first this equation. 1 over 1 minus x is equal to 1 plus x squared plus x cubed, so on and so forth, is equal to the summation of n equals 0 to infinity x raised to n. And the absolute value of x is less than 1. If we try to look closely on this equation, we are going to determine that this equation is a geometric series. And if we try to recall our lesson before on geometric series, we can have here wherein geometric series is convergent if the absolute value of r is less than 1 and its sum is represented as a over 1 minus r, which is completely the same with our equation here at the top, and the only difference is that we let a equals 1 and r equals x. Just remember this equation because we are going to utilize it on the latter part of our lesson for today. But now, let's just move on to our main topic that we are going to discuss. It is all about differentiation and integration of power series. It is important to understand that to differentiate and integrate power series, we can do so by each individual term, called term-by-term differentiation and integration. So let's now have our theorem. The theorem states that if the power series has radius of convergence r greater than 0, then the function f defined by f of x is equal to c sub 0 plus c sub 1 times quantity x minus a plus c sub 2 quantity x minus a raised to 2, so on and so forth, is differentiable and therefore continuous on the interval a minus r to a plus r. And we can able to get its differentiation and integration by getting the derivative and antiderivative by each term of the function. So for our f prime of x here, we have our first term, which is c sub 1. Because getting the derivative of our first term here, which is c sub 0, since it is constant, the derivative of the constant is always 0. So we're going to exclude that one. So we're going to move here with our second term, c sub 1 multiplied x minus a. Since we already knew that we have here the exponent 1, and by getting the derivative, we multiply the exponent to our constant here in front, which is c sub 1. So 1 times c sub 1 is also c sub 1. And after multiplying, we are going to subtract our exponent by 1 also. And we end up having an exponent which is 0. So any number raised to 0 is equal to 1. So c sub 1 multiplied to 1 is also c sub 1. That's why we have here c sub 1 as our first term. For our second term, we were able to derive it with the third term of our function here, which is c sub 2 times the quantity x minus a raised to 2. Since our exponent is 2, we multiplied 2 to our constant, which is c sub 2, which will become 2 c sub 2 times the quantity x minus a, and subtract our exponent by 1, we will end up with an exponent which is 1. That's why we just only copy here x minus a as our second term multiplied by 2 times c sub 2. And by continuing the process, we are going to end up with our representation here, which is the summation of n equals 1 to infinity n times c sub n times the quantity x minus a raised to n minus 1. Now let's have the antiderivative of the function. So for the antiderivative of the function, we have here our first term, which is c. Because when we are going to integrate the function, we always end up with an answer that has c. So we already written here as our first term, which is c. And our second term here, which is c sub 0 times x minus a. So we got that result by integrating c sub 0 here, because integrating a constant will also result to a constant. And our third term for our integration here is c sub 1 times the quantity x minus a squared over 2. So we were able to have that result by integrating the second term here of our function, which is c sub 1 times x minus a. Because when we are trying to integrate our exponent, which is imaginary here, which is 1, so when we integrate, instead of subtracting it by 1 for the derivative, we are going to add it by 1. So our exponent now will become 2, and the variable, which is x minus a, will be divided by 2. That's why we have here the result for our third term, which is c sub 1, the constant will remain, multiplied by our variable, which is x minus a, raised to the new exponent, which is 2, over the new exponent, which is also 2. And by continuing the process, we will end up with a representation here, which is c plus the summation of n equals 0 to infinity c sub n, multiplied by the quantity x minus a raised to n plus 1 over n plus 1, which is also our new exponent. And it is also important to remember that the radius of convergent for the power series that we have differentiated or integrated will remain the same with the original power series or function that we have. Let's now have an example here. Find the power series representation for ln 1 plus x and its radius of convergence. So for the solution, we have to remember the equation that I have shown you on the beginning of this video, which is 1 over 1 minus x is equal to the summation of n equals 0 to infinity x raised to n. So our goal here is to make our f of x, which is ln 1 plus x, to be in the form of the geometric series. So in order to do that, we will be going to get the derivative of our function. So the derivative of ln 1 plus x can be rewritten as 1 over 1 plus x. And to look completely the same as the geometric series, we will going to rewrite it into 1 over 1 minus negative x. And we will have these following terms here, which will be derived on this representation, which is the summation of n equals 0 to infinity negative x raised to n, which can also be rewritten as the summation of n equals 0 to infinity negative 1 raised to n times x raised to n. So by substituting any values of n from 1 or from 0 to infinity on the following representation, we can have the following terms written here. Okay, so the result here is the power series representation for f prime of x. But what we are after for is the power series representation for f of x. So in order to do that, we are going to integrate this one. So we have here the new equation, integration of f prime of x. So we are going to use this geometric series form, which is 1 over 1 plus x dx. And by integrating, we're going to copy all the terms written above, which is 1 minus x plus x squared minus x cubed, so on and so forth, times dx. And in order to get its integration, we will be going to integrating it one by one. So integrating all the terms here, we will have the result of x minus x squared over 2 plus x cubed over 3, so on and so forth, and don't forget to write c. And through these terms, we can able to come up with our power series representation right now, which is the summation of n equals 0 to infinity negative 1 raised to n times the quantity x raised to n plus 1 over n plus 1, which is our new exponent, plus c. And to have the final answer here, we are going to find the value of c. So to find c, we put x equals 0, and here we obtain our function, which is ln 1 plus x, to be ln 1 plus 0 is equal to c. Thus, our c right now is equal to 0 because ln 1 is equal to 0. So by substituting the value of c here in our equation, we are going to end up with a new equation, which is the summation of n equals 1 to infinity negative 1 raised to n minus 1 times x raised to n over n. So for our final answer, you have noticed that our index here is increased by 1. So why did we do that? It is because to simplify our equation here, our series above. So when we are going to increase our index by 1, we are going to subtract 1 also to all the n in our series. So that's why we end up negative 1 raised to n minus 1, and then x raised to only by n because it is subtracted by 1, and also over with n because it is also subtracted by 1. So as a result, this is now the power series representation that we are looking for, the function ln 1 plus x. And for the question of radius of convergence, since ln 1 plus x, the radius of convergence is 1, so therefore our radius of convergence is also 1. Okay everyone, that's all for today. Thank you so much for watching. Keep safe and have a great day.